Okay, hello everyone. Um, let's start. I'm seeing my audio levels are good, but if I can get confirmation in the chat there that you can hear me, that would be helpful. Um, Yesterday was kind of strange. There was some not audio bugs, but other bugs. There's always a few bugs. They're usually not even at my end. They're usually at YouTube's end, or maybe some connection issue. But that's okay. Let's start. Today, I'm just going to do a couple of problems, and these are problems which are similar to ones that are in your assignment. And you can see that this week and last week, we kind of changed up the schedule a little bit. I had you just watch a bunch of videos last week, and this week we did all the live streams because there's a bit of a learning curve to doing Newton's laws. Problems in Newton's laws, and the reason for that is that there's really it's not so much mathematically involved as it is conceptually involved. Okay, and even though I explain a lot of stuff in the pre-recorded videos, it's good to see me actually go over these things with you and show you the steps in which you do them in real time, and you can ask questions. Also, if you've tried the assignment and you have any questions from the assignment, I'll be happy to entertain those at this time too. Okay, this is kind of more casual. Uh, all right, yeah, thank you, Emily. All right, let's start off with the first one. The first one is I think it's like your first question on the assignment. I don't remember now, but it's basically one of these single box, so just one box, but on an inclined plane. Okay, a single box on a flat table is trivial. Okay, I have a 10 kilogram box. It's on a plane at 45 degrees, and the coefficient of friction is 0.35, and I want to know what's the net force and what's the acceleration. Okay, let's get the net force first, and to do that, that's really the where the diagram comes into play. You need a diagram because to get a net force, you have to add up all the forces, all the individual forces, and all the individual forces are vectors, so it's a vector sum. Okay, and so that's why it makes it a little bit difficult. So let me start off by switching to my other whiteboard, and we'll draw a diagram. So again, it's a 10 kilogram box on a 45-degree angle, and so what you do is just like with the kinematics problems, the first thing is just draw what you would see. Like you walk into the lab, and in fact, you're going to do this in the lab because you're going to do both static and kinetic friction in the lab. And so you just draw what you would see in like a lab. And so here's my inclined plane like this. And there's 45 degrees like that. Okay. So I guess you wouldn't see the 45 degrees. Oh, you might. You might because you got like a protractor. Like in the lab, there's a protractor that allows you to control the inclined plane. Okay. And then you've got a box like this. Okay. And here's the box. Okay, and it's sitting on the inclined plane like that. Okay, so there's step number one. Now, step number two is to identify all the forces, and I would go in order. I would go in the order of starting off with gravity first, and then normal, friction, and any tension. Okay, but gravity first. That's the important one. Okay, now we're going to attach all of the forces right to the middle of the box there like that. So I'm going to put a little dot there like that. Okay, now in reality, the force of gravity is acting all over this box. Okay, like at every point in the box where there's like a molecule or something, there's a force of gravity. But for these problems, you could think about the force of gravity as just acting at one point. In fact, later in the course, when we do rotational motion, we'll talk about this issue again, and then we'll have a much more sophisticated model for where gravity acts. But for now, we'll just attach all the forces as acting in the middle. And gravity, technically speaking, acts straight down like that. Okay. Now, you might as well start off and resolve that vector in terms of the component which is parallel and the component which is perpendicular to the plane. Okay, and the reason is because we got to do this vector sum. What you want to do is you want to form this kind of a cross so that all the forces or components of forces are either perpendicular or parallel to the plane. Okay, so I'm going to get rid of this and I'm going to replace it with a component which is perpendicular this way and a component which is parallel this way like that. Okay, so those two blue vectors there, they are the force of gravity. If you add them together, they would add up to the blue vector that I just erased. Okay, And you're actually going to do this in the lab. You're going to use a force table, and you might have done this lab already. I don't know where we are in the labs. But you might have even done this already where you've got these forces, a force table, and you see that if you've got two components, they're totally equivalent. Those two components are totally equivalent in terms of their effect as just the one. Okay. Now this one here is calculated by mg cosine theta. Okay. So that's how you calculate that one. That's the formula for that one. And this one is mg, and if one is cosine, the other one is sine. Okay, sine theta. Now, why the cosine is perpendicular and the sine is parallel, I'm not going to explain right now. Okay, I'd rather right now we just go through the steps so that we don't lose, don't get too bogged down in the details. But if you go back to the notes or the lecture, I explain why. And it has to do with making a bunch of right angle triangles in here. Okay, so the best thing for you to do is just memorize that when you've got an inclined plane problem like this, and only an inclined plane problem, the cosine is the perpendicular component and the sine is the parallel component. Okay, so we've got those two. Okay, what's in blue right there is the force of gravity. And then you say, well, what other force is there? Well, whenever two surfaces are touching, there's a normal force. And these two surfaces here are touching, even though I kind of draw them off, the box slightly above the uh, inclined plane. They are touching. And whenever you got two surfaces touching, there's a force which is perpendicular to those two surfaces. Perpendicular is called the normal, and so this is called the normal force. Okay, and it is perpendicular, but this other way here, like that. Okay, and that's Fn. All right, so we've identified our second force. Okay, and if there were no friction, we'd be done, but there is friction. And for the way friction works is that if this box is moving downhill like that, so this is the direction of my velocity, like there. Okay, so velocity is downhill. Friction is always in the opposite direction. Friction would be like that. Okay, and so if I draw that frictional force on the box like this, there it is, Ff. Okay, force of friction. And then you ask yourself, is there any other force? And no, there isn't. The only other force really would be like tension, but there's no string here, and so that's it. Those are all the forces on this box. Okay. Now, why are we doing this? Why did we even do this? And that's because we want F net. That's the whole point of this, is to get this magical F net like this. All right. Okay, and the reason we broke up everything so that it's either parallel or perpendicular is because, let me do this in purple here. The perpendicular components, this one only competes with that one. Okay, the two that are parallel, they have no effect at all on these two forces here, the perpendicular ones. So the perpendicular totally decouples from the parallel. So those two are going to compete with one another, and the parallel one is going to compete with that parallel one there, like that. Okay, so that's why we do it this way. All right, and to get that F net, and F net being a vector has two pieces. All right, let me switch to the to here, to the other whiteboard. Let me see if there's any questions. So feel free to ask questions or stop me if you wonder how, even if it applies to, like, you wonder how that applies to the assignment. I'll be happy to answer that. Okay, so where is that? Okay, over here. So we had the parallel gravity, and that was mg sine. I need a theta. Let me cut and paste from here. Is that going to work? Yep. Okay, mg sine theta. Remember, the parallel is sine, and that's going to equal m is 10. Okay, g is 9.8, but we rounded off to 10 just to make life easy, and then sine of 45 degrees, like that, and you crunch this through your calculator and you get 70.7 newtons. Okay, so there's one of them, and I'm going to put these on the diagram in a second, but let me do the calculation here. And then we're going to have the perpendicular component of gravity. That's the same formula, but with the cosine. That didn't work. With cosine replacing the sine. Okay, and that's going to be 10 times 10 times the sine of, sorry, the cosine of 45 degrees, like that. All right. And sine and cosine of 45 degrees is the same number. Okay, so there are some special angles that you should know, and I've given you some of those sines and cosines of special angles. I gave you some of those before, like sine of 30 degrees is a half, cosine of 60 degrees is a half. Sine and cosine of 45 degrees, they're equal to one another, and they're actually equal to 0.707. And so if you multiply that by 100, that's going to be 70.7. Okay, so if you say, well, why did these two numbers turn out to be the same? It's because I'm at 45 degrees. Okay, that doesn't always happen, obviously. Okay, and now we had the normal force and the force of friction. Okay, and you say, well, I don't know what they are. Right. So usually you wind up doing some calculation and then going back to the diagram and back and forth like that. So let's go back to the diagram, and let me now put those numbers in this diagram here. Okay, so both of the components turned out to be 70.7 newtons, and this one was 70.7 newtons. Okay, and so that's 2 of the 4. And now you say, well, what about the normal force here, like that? Okay, well, remember what I said earlier, that the normal force here competes with that force there. They're like having a tug of war, and they're pulling in opposite directions. Now, who wins? You can ask the question, who wins? And the answer is neither of them win. Neither of them can win, because if the normal force wins, if the normal force is bigger than the perpendicular component, that's 70.7, then this box would lift off the inclined plane. Okay? And if the perpendicular component of the force of gravity wins, well, then the box would dig into the inclined plane, and neither of those things are happening. And so neither of them can win. And so the normal force here has to turn out to be 70.7 newtons as well. Okay? So there's no formula for that. You just have to reason that out. And you're reasoning that out based on Newton's second law, or actually even Newton's first law, that says, if there's no acceleration, there's no net force. Okay, so in the perpendicular direction, okay, there can't be a net force in the perpendicular direction. In the parallel direction, it's a different story. Okay, but in the perpendicular direction, one of them can't be winning out over the other. They have to totally cancel one another out, and they do, because they're the same magnitude but opposite direction. Okay, and again, so that's just reasoned out. There's like, I don't know, no real formula that you use to do that. All right, and now the next one is that frictional force. So let me switch back to the other board here like this, and we have that this is now equal to 70.7 newtons, like that. And you say, how do I get the frictional force? And I don't have my mu character. I'll just write it out. The coefficient of kinetic friction, if you take the coefficient of kinetic friction and you multiply that number by the normal force, that's what gives you the frictional force. Okay, now to understand this equation intuitively, what it basically says is that, like, you see how this is 30.35, that's like 35%. Basically, when you have a coefficient of friction, which is 0.35, it basically says that the frictional force is 35% of the normal force. And the way to understand that intuitively is the harder the two surfaces press together, the more they stick together, the more friction there is. Okay, and so this coefficient of friction is kind of a measure of like how much friction you get for each unit of normal force, or something like that. Okay, so the normal force was 70.7, like that. And let me see, I think I've got my answer ready here somewhere. Where is it? Yep, I have that. It turns out to be 24.7, like that. Okay, so now we can go back to the diagram and just put that number in there. So over here, we can say, okay, well, this one turns out to be 24.7, like that. And now we can say, aha, this one's pulling downhill with 70.7. This one is pulling uphill with 24.7 newtons. Okay, maybe I should put the units in there. These are newtons, of course. Okay, so one is pulling downhill 70.7, the other one uphill at 24.7. And you say, well, which one wins? Obviously, the component of gravity downhill wins over the friction uphill. How much does it win by? Well, you subtract the two. So you do 70.7 minus 24.7, and I guess that's what, 46? And that tells you how much is left over. That's your F net. Okay? And so now we can go back to our other board here, and we can say, okay, so F net, what is that equal to? Well, this one was downhill, so this was downhill. This one, frictional force, was uphill. So these are the two that were competing. Okay, that one and this one here. And you say, well, which one wins? Obviously, the downhill wins. So it's that one minus that one. And that's going to give you 46 newtons downhill. Okay, so that answers our first question. What is the net force? And the net force is 46.6 newtons downhill. Okay, perpendicular, nothing, because there can't be. So this one, the perpendicular component of gravity and the normal force, they have to cancel, and we went through that already. All right, let's see here if there's any questions in the chat. Okay, and doesn't look like there is. Okay, so the next one is what's the acceleration? Now, the whole point, like, this is a lot of conceptual work. The whole point here is that the net force is really what you want to get to. So even if I'm asking for acceleration, really net force is kind of the bottleneck. Once you have the net force, then the acceleration is obvious because it's Newton's second law. And Newton's second law says that F net, maybe I should put a little underscore in there. Okay. F net is equal to ma. Okay, so Newton's second law is like, I think you can tell it's like the critical one for these problems. A lot of textbooks or whatever will just say F is equal to ma. I don't like saying that. I don't like saying F is equal to ma because there could be lots of forces, and to say F net is equal to ma reminds you that it's the net force. You have to do this. You have to do all the adding up of the forces to get the net force, because it's the net force that gives rise to an acceleration. Okay, so we don't want the net force. We have that. We want to solve for a, and so we isolate a is equal to F net divided by m, and what is that? That's 46 newtons divided by, it was 10 kilograms, like that, and that's going to give us 4.6 meters per second squared. And the direction has to be in the direction of the net force. Okay, so the net force was downhill, so guess what? The acceleration also has to be downhill like that. Okay, so that's our first problem completed. Okay, and I think that's is very similar to the first problem on the assignment. All right, so you proceed more or less in the same way. To be quite honest, it's I did it last week, so I don't remember all the details, but I do remember it was a single block on an inclined plane. All right, let me see if there's any questions. Everyone looks like they're happy with this. Good. Okay, now this one was with kinetic friction. Okay, the next one is static friction, and static friction always causes confusion. And so I thought I'd better juxtapose a kinetic friction with a static friction problem. Same, everything is the same, but this time it's static friction. Okay, and static friction means there's no acceleration. The box is being held in place by a force of friction. Okay, and so the first, I actually asked it in two steps, and I did this on purpose. Okay, first I asked for what the static frictional force was, how big is it, how many newtons is it, and the second one is what is the coefficient of static friction, and show that it's equal to tangent of theta. I actually proved that in one of the lectures. I showed that I didn't use any numbers. I just used like symbols, and I was able to actually derive that the coefficient of static friction has to be bigger than the tangent of theta. Okay, and so we're going to see that that actually works out in this problem, all right? But I wanted to actually get the static frictional force first, because to do static friction problems, it's almost like you have to do everything we did above, but backwards. So here, what did we do? We identified all the forces, and then we got the net force, like that, and then we got the acceleration. For problems with static friction, you actually start with the fact that there's no acceleration. That tells you what the net force is, and that allows you to calculate the sum of the forces that are on the object. Okay, and so that's a little bit more subtle. So it's like you're running the entire logic here in the opposite direction. All right, so there's no acceleration. Okay, right? Static friction. So that means that the net force is 0, right? And then you go, okay, well, what does that mean? Well, now we have to go to the diagram, okay? And so let me switch over here to the diagram. This diagram has gotten a little bit messy, so I'm just going to quickly redraw it. Let me create a new one here. All right, like that. There we go. Okay, and doesn't take that long to redraw this. Oh, that's terrible. There we go. All right, so here's the box like this. Okay, and it's a slightly different problem, so we have to go through all the forces again. There's still gravity. There's always gravity. mg cos theta and mg sine theta. There's still a normal force, Fn, and there's a force of friction, but I'm going to give it a slightly different name. I'm going to call it Fs, like that, because it's static friction. All right, and just like before, the perpendicular components will cancel, so that one, well, well, in this case they'll cancel, but they'll compete against one another in general. So Fn will compete with the perpendicular component of gravity, okay, and the parallel component of gravity will compete with the force of friction uphill, like that. Okay, in this case everything has to cancel. Okay, so unlike before where we were looking for Fnet, so it's like I asked the question, what is Fnet? Here we know that Fnet is equal to 0. Okay, so that's like actually like a starting point, and that tells you that this guy has to cancel that one. Okay, and similarly the other way around. Okay, so we can recalculate these values here, but they're the same as above because the mass didn't change, right? The mass didn't change here, gravity didn't change, and theta didn't change. And so it's still going to be 10 times 10 times cosine of 45 degrees, which turns out to be 70.7 newtons. And this one is also going to be 70.7 newtons. Again, because 45 degrees, sine and cosine are the same. Okay. And the normal force here is going to have to cancel that 70.7. So that's also 70.7 newtons. And last time we used the coefficient of friction to calculate the frictional force. This time we don't. We don't use the coefficient to find the static friction. Static friction is whatever it has to be such that it cancels this. And it's pretty obvious that it too must now be 70.7. So you can see we're getting a different number now. The logic is different and the number is different as well. Okay, so literally all four of the components are 70.7. All right, so this is usually a mistake that's made because students will say, well, you'll confuse like kinetic and static, and you'll go, oh, maybe I should use the formula that has static friction in it to calculate that. No, you just simply say, oh, whatever that is, whatever this is, it has to cancel this one. Okay, so that there's no net force either up or downhill. Okay, and so that's usually the point of confusion. All right, let's switch back here like this. And now I can write down all of the values. Let me just cut and paste out of here because not that they're all the same, but just to be very quick. That's still 70.7. That's 70.7. That's 70.7. And this one is 70.7 newtons as well. Okay, so they're all four components were 70.7 newtons. All right, and that answers the first question. Oh, and I guess we should call this static friction rather than kinetic friction. Okay, so that answers the first question. What is the force of static friction? And the answer would be 70.7 newtons. Okay, just to compare it, it was 70.7 newtons static friction, but it was only, what was it? It was 24.7 if it were kinetic friction. Okay, all right, so down here now, that answers that one. And now I say, show that the coefficient of static friction is given by the fact that, is given by, actually that's not the right way to say it. So it is not given by, but is greater than tangent of theta as we derived in lecture. Okay, so with static friction, here's another difference. Static friction is over a range. Okay, the coefficient is over a range. So I can't tell you the exact number. I just have to, I can only tell you what number it has to be bigger than. Okay, and that formula is basically this one. The coefficient of static friction must be bigger than or at smallest equal to the force of static friction divided by the normal force, like that. So basically, if the coefficient of static friction is bigger than this ratio, you're fine. It will not slip. If it's smaller, then it does slip. So this is the condition for the box to not slip. Okay, so if we plug in those numbers, which is pretty easy because they're both equal to one another, like this, you get 70.7 newtons divided by 70.7 newtons, like that, and that's equal to 1. Okay, and so the answer is that the coefficient of static friction has to be greater than 1. Okay, I can't tell you what it is. It could be 2, it could be 20, it could be a million, but it cannot be less than 1. Why? Because if it's less than 1, then it slips. Okay, so if it's 2, it won't slip. If it's 3, it won't slip. If it's 1.1, it won't slip. If it's 1.01, it won't slip. As long as it's bigger than 1, it doesn't slip. As soon as it's smaller than 1, it does slip. So that's why the coefficient of static friction, sometimes you can't determine exactly its value. You can only say its range, okay, and what it's bounded by. All right, so I did the two together because I think hopefully this is makes clear in your minds what the difference is between kinetic and static friction in terms of solving problems. Okay, so let's see here. I don't see any questions, so good. Okay, that's good. How many people are watching? 7 people. Good. All right. So, all right. Well, that was our first problem, and I think that takes us about halfway through the, a little bit more than halfway. I've got another problem. We might as well do it. Okay. And this, what I'm doing today isn't going to cover all the possibilities, so we're also going to have a live stream on Friday. But let's do another one. So this one is a 13 kilogram box, and it's sitting on a flat table. Okay, and it's going to move. The system's going to move, and so it has a coefficient of kinetic friction of 0.25, and it's attached to by a string to a 6 kilogram box, which is dangling off of the end of the table. And I could have even said with a pulley. Okay, but you've seen these problems before, so I'm not giving you all the details, and ask what's the acceleration of the system. Okay, and then I say part B here. I say repeat, but this time assume that the system doesn't move, and find the coefficient of static friction. Okay, so I don't know if we'll get through all of it, but I'll get as far as I can, and then this gets you most of the way through the assignment. There's just that last problem which has both an inclined plane and a dangling mass. So we'll do one of those on Friday, but let's start with this one here. So what's the first step? Draw a picture, right? And so 13 kilogram is on the table, and 6 kilogram is off the end. All right, so let's go here. New whiteboard. And what would you see if you were in the lab? You would see a table. Oh, you would see a table like that. you would see a box on the table like this. And this one is 13 kilograms. And you would see a box off the end like this. And this one is 6 kilograms. Then you would see a string attached like this. And you would see a pulley holding all of this in place. And well, that didn't turn out quite right, but you got the idea. This string should be up and down. I'm sorry about that. Here, try to fix that. Let's try it again. Like this, and there. That's a lot better. Okay, there we go. I've, I've actually got my mouse on my couch here, on a couch pillow, so it's not the best place, but I don't know. That's where I have my computer, so we'll work with it. All right, there's the first step, drawing these diagrams. The second one is to draw the forces, and you've got two masses now. You've got this mass here, and you've got that mass there, and so you're going to actually be drawing two sets of forces. In my notes, or in the pre-recorded lectures, I actually drew them separate from one another to not confuse them. But you could draw them both on the same diagram. You just have to be, careful that you don't confuse the two. Okay, so let's start off with the 13 kilogram box, and with the 13 kilogram box, there is gravity down like this. Okay, and this one's mg. And maybe we should do both mg's together like that, mg. But this is where confusion occurs, because really you should call one m1g and the other one m2g. Okay, and the reason is you've got two different masses. Okay, so sometimes students are just being careless, will say m1g and then put like 6 in here. No, this one is going to be the 13, okay, times 10. All right, and this one is going to be the 6 times 10. All right, so just be careful about that. All right, and so obviously this one's going to be 130 newtons. And this one is going to be 60 newtons. All right. Okay, so that's one force identified. What's another force? Well, for the box on the tabletop, there is a normal force, Fn. Okay. And for the box on the tabletop here, there's also going to be a frictional force. And it's kinetic friction. We'll call that Ff. Okay. And is there any other force? The answer is yes. There is, what color can I use here? I don't know, this color here. There is this one, which is the tension because of the string, Ft. All right, so that identifies all the forces. It names all the forces. It doesn't give a number to them, but it gives you all the forces there. And now you can try to actually see if you can find a value for all of them. Again, notice that this is forming that characteristic T. So once again, like this force, Fn, competes with that force. And this force competes with that force. Okay? And so you say, okay, well, can I get Fn? And you say, well, is the box levitating off the table? Is it lifting off the table? Nope. Is it digging into the table? Nope. So this force must cancel that one. Well, that means that this must equal 130 newtons, like that. Okay. And I just realized that there, if you can't see what that is, that's supposed to be an N, and I apologize. Just did not come out very well. But that's 100, this whole thing here is supposed to be 130 newtons. Okay? All right. So, whoops. 130 newtons. There we go. Okay, so 130 newtons. This 130 newtons here cancels that 130 newtons there. All right. Do we have FF? Well, yeah, we actually do. Let me do it over here. FF is going to equal mu k times Fn. Okay, and what did I say mu k was? I said it was 0.25. Okay, so that's going to equal 0.25, okay, multiplied by, that's Fn here, multiplied by the 130, and what's that going to equal? 130, whoops, 130 multiplied by 0.25, 32.5, 32.5 newtons. Oh, that's terrible. Okay, hold on here. Equals 32.5 newtons. That's why I like using the other whiteboard for math, but okay, we'll work with this. All right. And now, does this cancel that one? Not really. We don't know what FT is. We don't know what it is. Okay. And so we have to just, at this point, we could just say FT is equal to question mark. We don't know what it is. Okay. And so there's one of them that we don't know. All right. And let's now leave this aside for now. We've got 3 of the 4 forces on the 13 kilogram box. Let's see what we can do over here. For the 6 kilogram box, well, we got the gravity, 60 newtons, and the other one is going to be the tension up like that. Okay. And these two, that one and that one, they are equal to one another. And the reason they're equal is because of Newton's third law. Okay. Now the third law technically says that, for every force in one direction, there's a force in the opposite direction. Equal but opposite force in the other direction. Okay. And so you're saying, but wait a minute. Newton's third law says that this has to equal that one. But Newton's third law says that they should be opposite direction of one another. So this one's going to the left, to the right here. That one's going up, and that's not opposite. And you say, well, what's going on? Well, that's the pulley. The pulley is actually what's changing the direction. Okay, so really, to do a proper analysis of this one with Newton's third law, you'd have to include the pulley. That's too much. It's kind of annoying to go through that. So we won't worry about that. We'll just kind of use Newton's third law in its partial form, and just recognize that Newton's third law, when properly analyzed, when properly applied, we'll say that this FT is equal to that FT. In other words, the tension throughout the string is the same, which makes intuitive sense. Okay, but again, if we don't know this FT, we don't know that FT either. We don't know either of them. If you say it's equal to the 60 newtons, then that would be wrong, because then the system wouldn't accelerate at all. Because if this is 60 and that's 60, well, then they would cancel and there'd be no force accelerating anything. Okay, so that's not right. Okay, so there we go. All right, now what? Well, let's switch back now to the other board, and we can do things. I can do the calculations a little bit better there. So I'm taking a look at the chat here to see if there's any questions so far. All right. Oh, also, I hope I'm not going too fast, because, you can view this later, but you might be taking notes at the same time. Might be good to take notes, okay? And so over here, let me just write down what we found. For the 13 kilogram, we found that mg was equal to 130 newtons. Okay. We found that Fn, oops, let me do this. Fn here was equal to, why is this not aligning? All right. Fn was also 130 newtons, like that. Okay. And then the force of friction was, oh, I forgot. Let me see what was it? It was 32.5. Okay, it turned out to be 32.5. Well, let me write it out. It was the 0.25 multiplied by the 130, which is equal to 32.5 newtons. And we found that force of friction was unknown. And sorry, no, it was FT. FT was unknown, like that. Okay. All right. And for the 6 kilogram, oh, this is annoying me. Hold on. For the 6 kilogram, what did we find? We found that mg was equal to 60 newtons, and the tension force was also unknown. Okay. Now what? Well, the next thing is find the net force for each one of them. Okay. So F net there and F net there. Okay. And maybe I should switch back to the diagram just for a second to show you how to get that F net. Okay, so let's do the 13 kilogram first. Okay, so for the 13 kilogram, all right, let's look at the diagram again here. All right, so remember, these two are canceling. That one is canceling that one, so they're out of the picture. It's basically this one, FT, is competing against that one there. All right, and you might ask yourself, well, which one's going to win? Well, which way is the system going to accelerate? So maybe I'll do the acceleration, I don't know, in red here like that. Well, this one's going to be moving down like that. So it's going to be accelerating this way. And the 13 kilogram is going to be accelerating that way like that. Okay. And so it's FT that has to beat FF like that. And so your net force for this one is going to be FT minus FF. Okay. Again, these other two, the Fn and the mg, they're out of the picture because they're canceling one another. And so it's just going to be ft and ff. And the one that wins is ft, because ft's got to be bigger than ff. If ff were bigger, then the acceleration would be that way. Okay? And so because ft is bigger, the acceleration is this way. All right? So let's go back to the other screen here. F net has to equal the bigger of the two, which is ft, minus the force of friction in the opposite direction. We don't know how big ft is, so just leave it as a, leave it alone like that, minus the force of friction, which was 32.5, and there it is. That's the best you can do for F net. Okay, you can't go any further. All right, but you can say one more thing, and this is where the second law comes in. The second law, remember, says that F net is equal to MA, and M here, maybe we should say M1, A like that. M here is the 13 multiplied by A. And so you could say that this here that you found for F net, that's got to equal 13 times A. All right. Now I hope I didn't go too fast there, but just to be very clear, we found that F net, the best we could do, we could not reduce it to a number because FT was unknown. Okay, and so there's nothing you can do. I guess this is what makes this problem difficult, or one of the things that makes it difficult, is that you simply have to carry along this unknown. And this unknown is FT. If we knew FT, then we could subtract 32 from it and we'd have a number. But we don't. We don't know what FT is. And so we'll just say, okay, fine. I know the best I can say for F net is that it's FT minus 32. Great, so there's my F net. Like if F net is equal to MA, there's my F net. It's FT minus 32. And then it's MA. Okay, but because we got two M's in here, we're going to say this one, M1 here, is 13 kilograms. All right, like that. All right. I don't know why I'm obsessing about format right now, but I am. All right, there we go. Okay. So if we say that M1 is 13 kilograms like that, well then that M here, that M that goes into MA, that's the 13 kilograms. Okay, so that's 13 times A. And there we go. We've got an equation, and we really can't go any further with that. Okay, that's it. We could call that equation number 1. All right. So why? Well, because we're going to actually be able to solve with equation number 2 in a minute. But there's an unknown FT and there's another unknown A. All right. So this one, let's call this M2 like this. Oh, M underscore 2 is equal to 6 kilograms. All right. Oh, there we go. And now we say, what's F net here? So there's only two forces. Let's go back to the diagram and take a look. There are two forces. All right. And there's FT here like this, and FT is competing with MG like that, M2G. And you say, well, which one has to win? Well, look at the way that A is going. A is going down. 60 newtons has to be bigger than FT. If FT were bigger than the 60 newtons, it would be going up. And it's not going up, is it? It's going down. And so the 60 newtons has to beat the FT. Okay, so F net is going to be 60 minus FT. All right, so over here, we can say that this is going to be the 60 newtons, which is winning, minus the FT like that. Okay, and you can't reduce FT any further than that. All right. Now, the next thing is you say, okay, great. Now what? Second law. Okay. As soon as you've got FT, even if you don't have it as a number, sorry, not FT. As soon as you've got FNet, even if you don't have it reduced to a number, FNet, remember, is kind of that bottleneck. You get to it so that you can make use of the second law. You say, okay, great. Now the second law says that FNet is equal to M2A. All right, like that. And you can plug in for FNet. So right there, what's FNet? FNet is 60 minus FT. And that's equal to M2. What's that? That's 6 kilograms. And A we don't know. Okay. And there you go. There's your equation number 2. And you can now solve. The rest is just math, okay? And it's actually pretty easy math, because if you put the two equations one on top of the other like this, and you've got this one underneath it like that, okay, like that. Can you see that? Yeah, okay. Yeah, so you see how the two equations, one underneath the other, you can like literally add them. And so you can add the left-hand side to the left-hand side. So if we did that, let's add the left-hand side, so this side plus this one, okay, all right, and that's going to equal this one plus this one. All right, so you see what I did? I added this to that, and on one side, on the left-hand side, and on the right-hand side, I added that to that. And you could see that FT here is going to cancel FT over there. And so you get 60 minus 32, which is what, 26.5, is that right? Yep. Yeah, sorry, 27, 27.5. Okay. And that's going to equal 19 times A, like that. Okay. And that gives you an A of, divided by 19, 1.45 meters per second squared. All right. And I think that answers the question. Let me see here. I said, what's the acceleration of the system? And yeah, that's the answer. All right. So there you go. So the system accelerates at 1.45 meters per second squared, like that. All right. Any questions with that? Now, I said system, and not to introduce a mysterious word, but both, let's go back to the diagram quickly, both the 13 kilogram box and the 6 kilogram box, they both accelerate with the same A. So this A here is the same as that A there, which is why I said the system. In other words, the whole thing, including the string, accelerates at 1.45 meters per second squared. Now, why? Why does it do that? Why doesn't this box maybe accelerate more? Okay, like why doesn't it have a bigger acceleration? And the answer is it can't. If the 6 kilogram were accelerating faster than the 13 kilogram, then the string would be stretching. Okay, because this one, the 6 kilogram, would get further ahead, and so it would start to get further ahead than the 13, and then the string would be stretching. Okay. Conversely, if the 13 were accelerating faster, then the string would be shrinking or bunching up or something like that. And we're assuming a string which remains tight and doesn't stretch. Okay. And so both of these accelerations have to be the same. Okay. Which is why in the equation F naught equals ma, I could use the same A for both of them. You know, I didn't need like an A1 and an A2. So I like, like if they did accelerate at a different speed, a different rate, I'd call this one A1 and A2 because they'd be different, but they're not. They're the same, so we'll call them both A. Okay, so kind of a minor point, but it's important to understand the logic of all the pieces. Okay, so let's see, how much time do I have? Well, I guess I don't remember. Like technically, the class is supposed to end 5 minutes earlier or something like that than the usual hour, but uh, you know what? Let me cut the class here. Not because I don't want to go over too much more, but because maybe you should think about the static friction. And also, I want to pick up from this point here on Friday, because what I'm going to do on Friday is I'm going to do a very similar problem, but instead of putting it on a flat table and then have a dangling, I'm going to actually put it on an incline. So we're going to have an inclined mass on one side and a dangling mass on the other side. And there's also static friction there. Okay, and since static is also a little bit tricky, I think what I'd like you to do is maybe, just on your own right now, think through the static friction. Let me just give you a little bit of a clue on how to do that. I don't want to overdo problems for you. But if you go back to this, let's just think for a second. Remember what we did when we had static friction before? It's like we ran the whole thing backwards. And so if we run this whole problem backwards, static friction, what does that mean? So it means we don't know this one right here. So you could put an X through that one. Okay, so we don't know the force of friction because it's a different friction. Okay, but we do know that the system is not accelerating. And if the system is not accelerating, what can you say? Well, you could say that this force must exactly cancel that force. Aha, that's a clue. So if this force cancels that force, and this force is 60 newtons, then the tension must be 60 newtons. But if the tension is 60 newtons, then this tension must be 60 newtons. And if that's 60 newtons, then the force of friction must also be 60 newtons. Why? Because the two must cancel. Okay? So I kind of gave you the solution by speaking it out, but why don't you work through it, and I'll pick up from here next time, because I want this as an example for the last and third problem that I'm going to do on Friday. Okay, so let me just ask in the chat here and also ask out loud, is everyone okay? Any other questions before we end? And let me see. Well, no one's answering. Oh, you're good. Okay. Well, I got one answer. I can at least I know that you heard me. Well, you know what? If you guys are good, you got no questions. Let's just end the stream at this point. You can always ask me during the Google Hangouts in the evening. Work on this assignment before the like. Don't wait till the last minute, because it is a little longer than the other ones, and so you don't want to try to cram it at the last minute. You may not be able to catch me. All right, bye bye then.